Hey everyone. Right now I just want to explain a little bit about how the bits work behind the scenes of the various data types in Solidity, and we're going to look into some use cases of bit shifting and those operators, and we're going to look at how you can actually store smaller data types within larger data types. So, for example, if you want to save gas or something like that. But I really just want you to gain full control of the bits behind, for example, uints. So we're going to look at uints, we're going to look at ints, but it really applies to any other structure. But so, for example, in a uint, let's say the uint is 16. Okay, how does that actually look in terms of bits, and can we actually go in and get the individual bits and set the individual bits even, and so on. So we'll look at that. All right, so to the left, I'm in Remix. So this is where we're going to write our contract. And in fact, we'll do it as a library. And to the right, you can see I have some kind of, basically pictures available here so we can visualize what's happening. So in particular, let's just start with the uint 8 and see what's happening in terms of its underlying bits. So what I'm going to do is I'm going to represent a uint 8 in terms of 8 bits, and each box here is a bit, and I also show the index below. So it basically goes from 0, bit index 0, through 7, okay? So in a total of 8. So if you were to ask, like, okay, what does it mean if this bit is on? Okay, we can represent that with a black box. It means it's 1, and then a white is 0. Okay, so let's say that this is 1. Well, if this is 1 and the rest is 0, basically the way to get the decimal value of that binary representation is to take, 2, because we're always in binary, it can be 0, 1, to the power of the index in which the index of the bit, which is here 0. 2 to the power of 0 is 1. So the decimal value is 1. If instead we had this bit on, it would be 16 and so on. And we can show that with a black box there. So I just want to show you kind of the visual. So by black box, I just mean it's a 1. Okay, it also means that 1 is represented by this box up here. This one right here next to me. That one. Because the first one is set to 1, the first bit, and the rest of the bits is set to 0. So that's actually another way that Solidity behind the scenes would represent in bits this uint 8. Now I want to note also, look how I'm counting. I'm counting 0 from the right. I'm starting at the lowest from the right and going to the left. So this is just something in computer science called endian, basically how it ends. So there's big endian and little endian, just how it ends essentially, like where do you start counting from. So this is also called the least significant bit, this one all the way to the right, and the most significant bit to the left if it's in this particular endian. Okay, so that's just a little bit of a primer. It'll become relevant because we need to know how we should shift things around. Okay, so here's what we're going to do. We're going to write a library that allows you to build on top of uint 8s an ability to get their specific bits. So we will write code that, given any uint 8, okay, so this is a uint 8, okay, is equal to this. Okay, this is a uint 8 type. Okay, and we can fill it with some bits. So we can set this one to so this one to true, and this one to true right here. Okay, and those two being true is some value, some decimal value, right? And it's 2 to the power of 5 plus 2 to the power of 2. That's its value. So we will write some code now where we can actually go in and check if the 5th bit is, well, I should more say the 6th bit, but in the 5th index is 1 or 0. Okay, so we'll double check these things. Okay, so that's the purpose. So let's start quickly over here to the left. So we're going to do our initial Solidity. I'm not going to do the license identifier, but so it'll look like it's complaining a little bit there, but we're going to write a library and we're going to call it bitmath. Okay, and we're going to write also a contract that we're going to call bits or something. And in here, we're basically going to overload the uint. So we're going to do this using bitmath for uint 8. Okay, so it just means that whenever we use a uint 8 type in Solidity, so we do something like this: uint 8 my int or something, right? Like that. It just means that my int now inherits all the functions or methods essentially in this case from bitmath, right? And everything from there. So whatever functions I define up here, like function bit, right? It's a function, is a method essentially I can call on my int. Okay. So that's that. Now, all right. So we're gonna do this. So we're gonna call it bits, or just bit maybe. And the purpose of bit is to get the nth bit. Okay, like kind of index. Maybe we'll call it the ith bit just to make it clear that it's like an index from a uint8 that we send in. Okay, so we're gonna send in a uint8. We're going to send in a uint8. That's the data from which we're going to get the bit, and we're going to send a uint8. That's just the smallest like uint that we can have, and we're going to call it I. Okay, and we're going to say this is like an external function we can call, and we're going to make it pure because it doesn't really change any state or anything. It just basically returns the bit from that data, and then we're going to return that bit value, which we can definitely represent as a uint8. Again, it's just the smallest uint that we have, right? So first of all, we're going to say uint8 my int, or sorry, that's coming in the data. We're basically going to return data.bit, and we're going to give it index I. Okay, so we still have to write this function, this bit. We're going to do that up here. So what this does is when you call .bit on your uint8, it just returns that bit. So how do we do that? Well, first of all, we're going to have to take in the uint8. We can call it self. So that's just when we call that function on self, that self parameter, meaning the thing we call it on, this data, is actually passed in here as self on the call stack. And then we're going to take I, that's the index. All right. And we can make this internal because we're just calling it from this other contract as a library, and pure as well. We're not going to return any state. In fact, in libraries we should never really have any state. And then uint8. All right, cool. So this is where the actual logic goes now. Now we're going to have to, so the question is now, how do we go in and get the ith bit from a uint8? Okay. So this is where we're going to use the concept of bit shifting. So there's an operator in Solidity that allows us to shift the underlying bits by a certain number of slots, essentially. So what I mean by that is, let's say this bit is set, okay? So the decimal value of this uint8 here is 16, okay? I have these decimal representations of what each of these boxes mean, at least I show you 3, but the logic is the same, right? So decimal 16. If we were to send in decimal 16 here to this bit function and get an I equal 4, this would be 1 here, okay? And, basically the way we need to do it and the way it works is like this. We are going to shift the bits, the underlying bit patterns, and what the shifting does is basically you can think about it like this. We're going to shift it by 4. So what happens? Okay, let me first show you the operator and then I'll show you what it actually does. So we're going to do something like this. This is not the final code, but I'm just showing you the operator. So if I were to take self and then these two greater than signs followed by each other, this is the bit shift operator. You have to write 2 of these and 1. You're shifting the underlying bit patterns of self 1 over, okay, in the direction that they're pointing, like little arrows. Okay, so don't think about them like greater than signs. They're like arrows pointing to the right. Okay, so it shifts the bits of the operand to the left by like that operand's bit pattern by 1 to the right. Okay, and we can put other numbers here. We can say I want to shift you by 2 or 3 or 4. Okay, but if we just put 1, again, just an intermediate thing here, what's going to happen is the bit pattern is going to shift like this. So it's going to go like this. Okay, so now it's 1 box over to the right, and because so let's say we had something here. Maybe a better example would be to have that one as black. So basically set to 1. This is 1 and this is 1. So when we shift it over by 1, you can see what happens here is that, there's no such index as -1, right? So what's this going to do? Is it going to wrap around and come back around here? No, it doesn't, which is good. That would be confusing. What it does is it actually just cuts it away. Okay, it just cuts it away. We actually just lose this one bit. Done. What happens on the other end? Now there's only 7 long. Well, I mean, behind the scenes, I mean, you know, it's just going to be set to 0, basically. Just think about it as being set to 0. It's not like we actually have a thing that's 7 long. It's still 8 long. It's still uint 8. But just think of it as something coming in from the left. We have an infinite supply of these zeros that just, right? Because that's it's always like 0 if it's not set, right? I don't know if that was confusing, but the point is just that we're shifting it over, and we're basically, imagine underneath here, this is 8 long, that you actually have an infinite string of bits, but we're just focusing on 8, and you just shift it over 1. It doesn't mean that like this side goes away. All right, I hope that's somewhat clear. The point is just a new thing comes in. Cool. And we cut this away by shifting it over. Notice also that this bit we're interested in the 4th position, actually sits here now in the 3rd position. That's interesting. And I'll show you why the goal. Okay, so what's the goal here is to actually move this bit all the way over to the right. If we can get it to sit right here, the bit in the 4th location, if we can get that moved over here, then after that, we can return it. And I'll show you how to do that. It's not trivial. It's not like we can just, there's no operation or something that says return 1 bit in Solidity. We still have to do a little bit more stuff, but that comes next. Okay. The point is just I want to move this over now, the 4th here, over to position 0. So what we're going to do is we're actually going to move it over by 4. Okay. And again, I'm going to generalize it in a second. But if we move it over by 4, what actually happens is we're going to move it over another step. Okay. So we'll clear this bit. This happened to be 0, so it doesn't really matter. And so on. We're going to just keep doing that, right? So I'll just do that twice now. So now we've done a total of 4 times. We have the 4th bit. This is still the 4th bit. Okay, but it's in the position of 0 now. Okay, but it's still what was sitting in 4 because we shifted it over 4. So now we have that 4th bit right here. Great, because now the question is how do we return it? Because note that we could still, let's say the 6th bit from the beginning was also set. This means that this is now set. We shift everything, right? The 2nd is now set. So this is how the pattern looks now. This is the top one shifted by 4 bits to the right. That's the bottom one, okay? Okay, we don't care about this bit in the 6th index. We just want the one in the 4th index. Okay, so how do we do this now? We only have shifted it up here. Okay, the way to do that is you basically create a new bit pattern that's 1. Okay, this is uint 8 of 1, right? Right, because 2 to the 0th is 1, so that's 1. The rest is just 0, so it's just 1. Notice how this 1 will always have its first box here set to true, set to 1, right? And the rest will always be 0. That's just how 1 is represented in all uints and ints and so on. Okay, great. So what we can do now is we can actually do an AND operation. Okay, so AND operation right there between these two. If we do an AND operation between these 2 boxes, okay, like this, you AND these 2 together. Well, AND takes in 2 bits and it's going to AND them together. And if it's one is 1 and the other is 1, it's going to combine to 1. Okay, because it's A and B, and that's true. They're both true. If you do 1 and 0 like this box, you're going to get 0. So this is like a mask, basically. You can treat this as a mask that only will return the bit that's in the first index here, and will set everything else to 0. Okay. So after you AND these 2 together, you will be left with, well, you'll just be left with this, with 1, basically. Okay? That's what that is equal to. And if the 4th bit up here had been 0, this would have been 0. Like that. This would have been 0 as well. But now that we've ANDed the 2 together and it happened to be 1, well, it's 1. Okay, so this is now the 4th bit from the original uint 8 in index 0, and no other bits are set. Okay, so that's what this is. Okay, so now what we need to do after we have the 4th bit in index 0, now we need to like actually return this, but that's easy. That's just, we can just represent it as uint 8. We can't really, there's no like uint 1, for example, in Solidity, right? You know, we let it, like I said earlier as well, like we can't really like return 1 bit. Okay, there's no such thing. So anyway, so this is actually just a representation of that, but this will tell us what's in the 4th location. So I hope that's all clear. So the bit shifting can just kind of, it'll just shift everything over, and everything falls off a cliff here, if you will, right? If you shift it to the right, it's like it's falling off a cliff, and we can't recover it. It just disappears and gets cut. And something else from the other side comes in, right? So that's what happens. All right. So anyway, so in general, let's shift it over by I so that we can just generalize it and say instead of just for, we can do whatever we want. So we're going to shift it over by I, and then we're going to do this AND operation with 1, but we're going to do a uint8 on 1. Okay, we're going to have to cast it to the right type. We're going to return this. Okay, and that's what we're going to do. And right now, we need to be careful with precedence. Okay, so what I mean by that is we need to make sure that it shifts first and then does the AND operation. So the question is this operator, does that have higher precedence than this operator? Okay, does the bit shifting happen first and then the AND, or opposite? The way you answer that in general, I just want to show you how to answer that in general, is to search for the precedence of operators in Solidity. Okay, so this has precedence 1. The top is the most important and the bottom is the least important. So what I mean by that is we need to figure out whether the right, like whether the bit shift to the right is higher in this list than AND. Okay, so we just scan through it from the top, and we're going to find the shifting, the bit shift. See, bitwise shift operators happen with higher precedence than the AND operator. Okay, so it means they happen first, and then the AND happens. Okay, so this is actually okay, but what we can do to make it maybe more readable is this, because putting in parentheses is the highest like precedence basically. Like this will always happen first. So just to make it more clear, maybe we'll do that. But so in general, that's how you check and answer that question. Okay, anyway. So now what we're doing is returning this. Good, all right. And then we have our main function down here that gets the ith bit from the data. Okay, so I hope you're building intuition now around why are we writing it like this? What are all these weird symbols with the right, and the and all this stuff? That was visually what was happening over here. Okay? Okay, all right, let's actually try to deploy this. And it's going to complain a little bit, the compiler, it's just a warning. We're also going to have to make sure that we get the right contract here. The top one is just the library. So we'll deploy that. Okay, so that deployed just in our local VM here in Remix. All right. And then what we're going to do is we're going to send in data, and let's send in 16. Okay? 16 will have its bit in the 4th position set to true. And we're then going to get the 4th bit. Okay, so this should return 1. So you see it returns 1. Now let's try again to send in 16 again, but we'll get the 0th bit. Okay, so how does 16 look up here? 16 looks like this. Okay, this is what we're sending in. This is 16. Okay, it has only 1 bit set to true in the 4th index, and the rest are 0. Okay. So now we're getting the 0th bit. That means we're not going to shift it. I mean, we're going to shift it by 0, which means we're not going to actually change this at all. We're going to AND that with 1, which has a true in the 0th index, and we're just going to return that. But since 0 and 1 is 0, when you AND them together, it's going to be 0. So when I click this, it's going to be 0. Okay. We can also get any of the other bits. 1 is going to be 0. But notice that we're actually X-raying. It's like we're X-raying into the underlying bit pattern of the uint8. We're actually looking at how do the individual bits look right now, and everything is 0. See, I'm clicking this 0, and I'm going to skip 4. We know that's 1, and then there you go. Okay, so everything is 0 as expected. Great, so that's how you get the bit. All right, so now these operators should, I hope they make a little bit more sense. We can also set a bit. Okay, so let's say that self comes in and we want to set the bit to true in location I. Okay, now I'm just going to make some simplifying assumptions here. Let's just say that it is 0 to start with, and we're just setting it to 1. There's a way to toggle it as well, so that if it is 0, it becomes 1, and if it's 1, it becomes 0, or always make it 1 no matter what it is. Okay? I encourage you to try to write that code, but I'm just going to simplify some stuff. So I'll just say I want to set the bit in location I to true. Okay? So in this case, what do we need to do? In this case, let me show you here. We have our uint8. Okay, let's say it comes in with 0. Okay, and what we're going to do is I want to set an arbitrary bit to 1. So what we can do actually now is kind of the reverse of what we just did. We will introduce, or we'll introduce 1. That's kind of our base unit, because we know that always have its bit sitting right here in location 1. So that's a good starting point. And what we're going to do now is the opposite. We're going to shift to the left now, this one bit to the left by how many we want, like so 2 or 4 or whatever we want. And then we will not AND them together because we're assuming this is 0. We will OR them together. Okay. All right. So what do I mean by that? What we're going to do is we're going to shift this left by, let's just say we do 4. Okay. What happens when we shift left? Let's just focus on this right now. Shift left for that one. Okay. Again, this is going to go in by 1, 2, 3, 4. It's going to go in here. Okay. Like that. Once we shifted it 4, then we're going to create not an AND operation this time. We're going to create an OR operation because we want, this is 0, this is 1. 0 or 1 is 1. Everything else will be 0. 0 or 0 is still 0. Okay, again, we're assuming this is 0 all to begin with. There's a way to fix it if it's not, but anyway, just to simplify. Cool. So what we're going to do is we're going to take our pattern self, which is this top one that's all zeros. We're going to OR it together with, and I'm just going to create a parenthesis now, with this, like this final thing, which came from doing what? It came from doing a uint8. By the way, we need a uint8 here. A uint8 of 1, right? We did a 1, and then we shifted it left by this many indices, right? Okay, so that's why this is a bitwise OR operator, by the way. This is just taking the OR of each bit separately along, like for all 8 bits. Okay, so that sets the bit. So now we can actually set the bit as well. So we can go down here and say, I mean, we can just create like a general function down here. Yeah, so uint8, data, uint8, I, external, pure, returns uint8. All right. So I'm just going to call this bitmath, and basically it just means I can do now, for any incoming data, I can do data.set bit of the index. Okay, and again, it'll return data for me. So I'm going to update the data by setting the bit and like that. And I can just return that if we want. So it'll just return the bit pattern with the ith bit set. Okay, all right. So let's try to deploy this. And yeah, let's try to deploy the contract, not the library. There you go. And basically, okay, now we're going to try to do bitmath. So we're going to try to send in 0, but we're going to try to set the 4th bit, okay? So we're sending in 0 and we're setting the 4th bit. What do we expect? The 4th bit index, rather. We expect 16 to come back, and that's what comes back because we just did this. This is the pattern we ended up with, which has a true in that location. Okay, so that's how you do that. So now you can set the bit, and this is kind of cool because it means you can store whatever information you want at the bit level. Okay, so let's say that you assign some meaning to these bits that were beyond the basically, you know, like you said, oh, if bits index 0 is true, that means you know, I don't know, let's say it's a game or something. That means I have a stone, and you know, this bit index over here means, you know, I have a sword as well, you know, things like that, right? It's just much more compact because you don't need like especially like you don't need separate booleans like, do I have a sword, true or false? That'll take up a full word. That'll take up a full like 32 bytes. So basically, you can do it extremely compact at the bit level. You can even do like multiple bits have a meaning, right? You can say these 3 bits together have a meaning depending on what they are. Okay. So this I'm hoping that this will just give you full control. It's basically like, you know, your Neo, right? You see at the bit level. You have maximum, you can store whatever you want at the bits and make sense of it. All right. So the other thing I just wanted to show you was is kind of like, so now we're setting bits, we're getting bits. Now I want to show you a little bit about how we can pack things in there. So let's do this. Let's say we have a uint 16, and that's right here. Okay, let's say we have a uint, or in fact, you know what? Let's change it. Let's say we have an int. Let's say we have int 16, because then we can get to the topic of signed integers as well. Right now we just did uints. There's a subtlety around signed integers. So Solidity uses to's complement to represent negative numbers, and we're going to see how that plays in. So just the final thing I want to chat about here is let's say that we had a 16-bit pattern, so a uint 16, or sorry, an int 16 rather. If we have an int 16, and let's just say we wanted to pack in some information in the first 8 bits, like an int 8. I want to store an int 8 in here, and I want to store another int 8 in there. Now, one way to do it, you can do it with structs, right? You can do like an int 8 and then another int 8, sure. But I just want to show you, since we're on this topic, and this is more general as well, because what if you want to store like something in the first 4 bits and then something in these 2 bits that have meaning, like those 2 bits together mean something, and so on. So it's more general to be able to do it at the bit level, okay? But let's say, just for sake of simplicity, we have an int 8 and we want to store in each of those. Let's write that function. So let's go over here and say, I don't know, bitpack, maybe. And we have, let's just say, yeah, maybe let's just say int 8 left, int 8 right, okay? So this is like what we're gonna write in the left. Actually, yeah, maybe you know what? Maybe we'll like return this back. So I'll show you in a second. So we're gonna bitpack that. We can also override, or we can also overload here the using bitmath for int 16. We can do that as well, as long as we just don't call any of the functions that take in the uint 8 here as self on the int 16. We're fine. We can actually include those functions up here as well. So what I mean is we can say to left. Okay, to left means I'm going to take an int 8 that comes in. Sorry, I'm going to take the data I'm operating on, so self, and I'm going to take the left data coming in. Okay, I'm going to also make that internal pure, and it's going to just return that self but modified. Okay, so I'm going to now take an int 8 in, and I'm going to store it in the left side. So what are we going to do? And notice, by the way, when you have 16 bits, of course, like the highest bit become a lot larger. You take 2 to the power 15, and that becomes 32,000. Just a note on that. But anyway, so great. So what are we going to do? We're going to take in an int 8. So it's still going to take up this space here. And again, it'll have some bits, and I'll just show you a general pattern there. Okay, it's going to have some bits like that. It's going to look this way. What are we going to do? How are we going to store it in the left side of this? Well, we just learned about bit shifting. So how about we just take it in at the beginning? You can always think of it, it'll always start at the least significant bit. So everything always starts over there. It's always, that's the starting point. So we're going to have to slide it over here. There you go. Like that. We're going to bit shift it over by 8. Okay? And then it'll be positioned in this spot right here. Okay? That's all it is. So now you know why, and you know how to do it. Because to bit shift something left by 8, well, you're going to take the incoming thing, and in this case, let's just do self plus, okay? So I'm again assuming it's like 0 to begin with, nothing sits there. This could be a useful case if you want to add to something and keep adding to the left side, more numbers further down the line. So in general, I don't know what's the best way to write this. I'm just assuming I want to keep adding to this part. But as I said before, there is a way to just delete what was already there, right? You can mask that part with zeros. We'll actually get to that in a second. And then add in the new stuff. That's how you would clear it and rewrite, so to speak. But let's just say we want to add. So I'm going to take self, which is the full 16, and I'm just going to add in what comes in, and that's left. But I'm going to shift it over by 8. Now we have to be a little careful, because let's go over to the precedence. Is plus higher than bit shifting? Okay, we actually see it is. You see this in position 5? This plus sign will actually be executed first. So what's going to happen, it's going to take self plus left first, and then shift the result by 8. That's not what we want. We want to shift left by 8 to the, we want to shift this left number, this int 8, by 8 bits to the left, and then add it. Okay, so it sits over here, and then we add it together. So when we add it together, after we shift it, it'll be over here. And this, of course, will be true, and that will be true. Okay? So that's it. We've stored an int 8 in the left part of an int 16. That's kind of cool. It gives you kind of much more control of the underlying bits, right? All right. So I'll just do this down here. I'll say int 16. We'll say my int. It'll start at 0, but I'm just going to explicitly show it here. No need to do equals to 0, but I just want to make it absolutely clear. My int, again, we're going to operate on it and return it. So I'm going to say my int equals my int dot to left. I'm going to send something to the left. I'm going to send this data to the left. So we're going to make that update. Cool. All right. So now another thing we want to do. All right, and then return my int. All right, cool. What we're going to do now is write a function that returns the right and the left side. Okay. And another thing I just wanted to mention was, so like this. Okay, I'm going to write these functions left and right. We don't have them yet, but it's just that it pulls it back out, these two halves. Another thing I just wanted to note up here when we do the two left. This might give an issue because self is an int 16, left is an int 8, and you can't really add these together. So we need to upcast this one to an int 16. Okay. But what's going to happen when you upcast an int 8? Here's what's going to happen. So this int 8 comes in. It sits at the very end. Okay, that's always how they start. Like all data starts from this end. Okay. So what's going to happen actually is that when we upcast to an int 16, it's just going to look like this. Okay. And now they're just compatible, so that when we shift this over, we're still going to shift that over. They can be added together because of the type. Okay, now in this case, this to the left will fall off, and something else will enter from the right, and basically look like this, right? Fill that path from the right. Oops. Okay, just making that clear, and another box here. All right, so cool. All right, so you just want to make sure they're the same type in general when you add things together like that. But other than that, that's just a small note there. Okay. Now we need a function that can actually get the left side. So we're going to take in an int 16 self, and we're just going to return the left side. Okay, so we're going to do internal pure returns an int 8, right? Because that's an int 8 is going to sit in the left side. How are we going to return the left side? Well, by now I think we have a good grasp of this. So our pattern is going to look like this. I'm going to kind of get it close to this so we have the indices. We're going to take the 8 here. Okay, the 8, and since it's sitting in the left side, we're going to just have to slide it over to the right. So we'll slide it over to the right like that. Okay, and I can just represent that by doing this and just like swapping places here essentially, because that new fresh set of zeros will come in from the left. Okay, so we're going to slide it all the way there, and then what we're going to do is just return an int 8. Okay, so let me talk just a second about that, because I don't think we'll cover that. If that's an int 16, okay, right, 16 bits right here, that's an int 16. If I downcast that now to an int 8, what's going to happen? What's going to happen if I downcast it? What's going to happen is it's going to basically just behind the scenes cut everything away except the first 8 bits. So it kind of does the job for us, this downcasting. We don't need to do anything else. We just shift the final 8 bits over to the front, and then we just downcast it to an int 8, and it'll just cut away everything. Okay. All right. So what did we say? So to get the left side, we need to take self and shift over to the right. We need to slide the left side to the right side, because the right side is the beginning. We're going to slide it over by 8. After we've done that, we're just going to downcast. Because like I said, that removes those final bits that we didn't want. Okay, and that's it. That's the result. So that's how we get the left side. Cool. Now we need to get the right side. Well, that's even easier, because the right side has, I mean, as I just said, by downcasting, right, in comes an int 16. We're just going to return the right 8 bits just like we just did here. So all we got to do is just downcast it to an int 8. That's it. That will cut everything that sits above it. So even though stuff was sitting up here, like the left side was filled with bits over here with some bits, this int 16 downcasted to an int 8 will look like this. The first 8 bits, which is exactly what we want, that's the right side. It'll just cut away the rest when you downcast like that. So that's why in general downcasting is dangerous. You want to check that, in this case, we don't care. We want to lose the left side, but I'm just saying in general. All right, anyway, that's how you get the right side. So we only have in this bitpack one functionality right now we can write to the left side. Okay, so let's try, but now we can return what sits in the left and the right side. So when we write to the left side now, whatever comes in as the left argument should just be returned again as the first parameter from this function call. because again, we call left as the first. And the right, well, we're not really doing anything with it right now, but we're still going in and seeing what sits on the right side, which should be 0. So it's a way to check that we're not overriding the right side or anything when we do this. Okay, let's see what happens. Let's go to the contract. Bit pack. So left, let's write, I don't know, -1, and let's write 0 to the right side. I mean, it doesn't matter what we put in for the right. And we're going to get left, or what we're going to get in return is -1, which is the left, and 0. So notice that that was the left side and the right side indeed. Okay, let's try to write, I don't know, 20. And we get 20. Okay, so this is working. Now, let's actually implement storing to the right side. So here, we're going to do, this one actually becomes subtle. And I'll tell you why. This one does become subtle. So if it was uints, it would be pretty easy. Pretty straightforward. There's no gotchas. With ints, there is a gotcha. Okay, so I'll tell you why. So, okay. If I have a negative number, the way that this is represented on the computer and in Solidity, and really by far most programming languages, is using something called 2's complement. What this means is that if you have a pattern like 0, 0, 0, 0. Okay, this is 1 with these like 8 bits here. Okay. How do you write -1? Okay, we know this is 1. Let's say this is decimal 1. Okay. What is the bit pattern? We're gonna write. What is the? If I have -1 here, what is the bit pattern over here for -1? Right. That's a little interesting because you can't. You can only have 0 and 1. So how are you going to represent -1? Okay. So the way that it's typically done to represent a 1 is that you say, I want it represented in such a way that that this bit pattern, which is 1, plus whatever bit pattern -1 is. Again, we are to discover that soon. Whatever bit pattern -1 is. I want to be left with 0. So I want the property of the bit pattern. And again, you don't have to follow this rule actually. Like you can do whatever definition in the compiler you want and everything. Like you don't have to follow this rule, but this is called 2's complement, where you're saying, I just want 1. I know how 1 looks, and I want, when I add that to -1, like the negative version of itself, I want this to just be 0, which is fair, right? 1 plus -1 is 0. And the same for any other value. Like if I had 2 and -2, I want that to be 0 as well. Okay, so what's the answer here? The answer is that -1 actually needs to be represented like this. So let's put -1 here. Well, let's see what happens. When we add, let's start here. Let's just say we represent it like this. What would happen? We would add 1 and 1 together, which would actually give us a 0 here. So that's great. But 1 plus 1 in binary actually creates a carry, right? Because we're above the highest we can represent. There's no 2. It's not like 0, 1, 2. 0, 1. So once you do 1 plus 1, that's like doing 5 plus 5 in decimal, right? You're going to hit 10, but you can't store 10 in a single unit, right? You need to go to the next placeholder, if you will. So in this case, this will certainly get 0, but we're going to get a carry of 1, so this will be 1. Okay, that's not what we want because this is not 0. Okay, but what if we then added to that another 1? Okay, so now 1 and 1 is 0. It carries a 1, but that gets added to this one, so that's also 0. But now it gets carried over here. Okay, but that's interesting because we just moved this. We don't like this one, but we just keep moving it to the left by adding 1s up here. Let's try again. Let's add 2 more 1s. Okay, it's going to be moved again. Okay, and this time it's going to go all the way over here. Okay, just by doing that. So you see the pattern. We'll basically just need to add 1s. And I want to describe to you, at this point, we've moved the 1 all the way over here. Now, this is still not 0, so we actually need to move it again. And what happens when we move it one more time? What happens when we move it one more time is interesting because it actually falls off. So it's important to understand that these bits, it's kind of like a circle, if you will. Well, it's like What's a better way? It is like a cliff, I guess, right? Like if you have 1 plus 1 at the very left side, you're gonna get 0, and you technically will have a carry, but there's just not enough bits left to represent that. So the carry goes away, the bits go away. That's it. You're left with 0. It just disappeared. Okay, because you don't have enough space. So it's not like the computer underneath goes in and says, "Oh, I realize the carry is beyond 8 bits, so let me allocate another couple of bits for you." No. That would also be very confusing for you as a programmer. Okay, so you should know this. Okay, so what is this? This is obviously 0. But the crazy part here is that -1 is represented by all 1s in 2's complement. Okay, so so that's it. If you had 2, you can then also guess how that would be represented, because you would have a 1, 0 there. So what added to this would give you all 0s? Well, this is already 0. So the -2 have to look like this. 0 plus 0 is 0. I'm happy with that. 1 plus 0 is 0, and then it rolls over. You see that? So that's kind of how that would be represented. So that's kind of how it looks. The point is, the reason I'm just bringing this up is that this has an implication for the way we're doing this. Because if we want to assume that an int 16 is coming in, let's get a fresh int 16 here, like that. And we're going to write first to the left slot. We're going to write this pattern. It doesn't matter what the pattern is. I'm just going to say, I'm going to write this pattern. Boom. I stored that in the left. And I can make a divider here to make it clear. This is where the left and the right side split. Okay, so everything to the left of this red line is left, and so on. Okay, like that. Let's say we stored the left side first, and now we want to store something in the right side. And we're doing it using this plus approach. Okay, let's first write the naive way potentially of doing it that would work with positive integers. Okay, how do you store something to the right? Is you just say self plus int 16 of right. This is the naive way. You take the incoming int 8 right. Yeah, I mean we have another function called right. Okay, we can underscore it just to make the compiler a little bit more happy. And technically the same with left. I don't think it's strictly necessary, but we just want to be like good citizens there. All right. So technically all we have to do is take the incoming right, upcast it to int 16, and just add them together. So what that means is in general, or not in general, rather only for positive numbers, what happens is that if the int 8 comes in, and this is the right side, and I want to add these together, I can upcast this int 8 to int 16, and what that will look like is when I upcast it, they'll just be zeros when it is a positive number, and I'll just add these two together with the plus sign. So it just means like 1 and 1 becomes 1 and so on. It's basically like an and. Okay, and then that just means that all this stuff will it's like I'm loading that int 8 into that slot to the right. So great, everything is good. Now, what happens? So this works for positive numbers. Of course, since we're using ints, we should also handle negative numbers. Like I just said, the 2's complement. Remember how it puts a lot of 1s in the higher bits, and it'll actually just keep having 1s to the end so that you can keep pushing everything out and make everything 0. Remember that, how we just went through that 1 plus minus 1, and you had to kind of just keep adding 1s in the minus 1, and it became just filled with 1s. If you have a negative number, like int 8, let's just say that was negative, what you're going to find is when it comes in, let's start up here, you're going to have a lot of 1s in the negative number, right? So let's say that this is a negative number right here. That's what comes in. When you upcast a negative number, int 8 to int 16, so this whole thing is now int 16, right? When you upcast that, what's going to happen? What do you think is going to happen? Do you think it'll just, when it upcasts, it'll just, have 1s here, and that's it? That's how it's going to look? No, it'll keep continuing the 1s because Solidity thinks, well, you have a negative number in int 8, like -1 or something, and you want to upcast it to an int 16. What it's going to do for you is actually put 1s in the place of all the higher bits, so that it keeps being -1 just in int 16 representation, which has a ton of 1s up here. Again, because it has to do that 2's complement. Okay? So what would this do? If you do 2 right with a negative number, it means that it would actually add to the left side. It would encroach on the left side's bits because it does this stuff. Okay? So how do we write a negative number to the right side? Well, we're still going to upcast it so that we can add them together so they're compatible. So we have this situation here. And the question is, how do we add these two together so that where the red line is, we don't add the bits to the left of that red line in the incoming write data. Okay? Okay, so what we'll do is we'll first upcast it like this, and then what we're going to do is set all these to 0. So the question is, how do you do that? What we can do is we can AND those bits with a mask that's 0 in for those bits. If we do that, these will all turn to 0. And this, by the way, will still be 1. So it'll still be a valid int 8, like a negative number. It's not going to be a valid int 16 for sure, because we're going to set these to 0. But it'll still be a valid int 8, which is all we care about. Okay? So the way we do this is to AND it with a mask that's 0 in these locations. So we're going to upcast it to int 16. And what we're going to do is we're going to AND it with a mask. An easy way to write these bit masks. So the question is, like, how do you write a bit mask? Like, do you write like ANDed with, you know, like 0, 0, 0, you know, and so on? Well, it's actually easy just to do it in hex, like numbers or characters. So what I mean by that is, in Solidity, you can do this 0x and you can do 00ff. Okay, so what does this mean? Each hexadecimal character, so for example, the 0, is 4 bits. 2 of them is 8 bits and basically a byte. Okay, so what you can do is you want this, like these 8 bits to be 0. Okay, so you want that. And you want these 8 bits to be like whatever they are. Okay, so we're gonna AND this together, and the way we do that is AND this with zeros, and that's what this is. These 8 bits here, okay, are all 0, and then we're gonna AND this side to the right with 1s, which means that it'll just look itself. Like this ANDed with 1 will just mean wherever it's 1, it'll still be 1. Wherever it's 0, it'll still be 0. So that's what these Fs are, okay? F, like when you AND something with that in hex here, it'll just be itself, like it's like ANDing with 1, okay? Cool. So what we're gonna do is take the incoming write pattern. In case it's negative, it'll have a lot of bits to the left, like towards the most significant bit. We're gonna upcast it. That means we're actually introducing a lot of bits we don't want. That's this whole region. We're gonna cut those out by ANDing with a bit mask. The mask that's 0 in this region. So how does the mask look? The mask looks like this. It's 0 up there and it's 1 down here. This equals 0x00ff. That's what this equals, this right here. You AND this with this, oops, and you're gonna get basically just the right side. Okay, and you're gonna add that to the right side, and that's it. So I just wanted to explain that complexity. Why did we not have to do all this stuff at the left side? Well, because the incoming left pattern might have had all these bits to the left for sure. But then we shifted everything to the left anyway. So it fell off the cliff anyway. So it didn't matter, and it didn't overwrite anything to the right. So it's only the one to the right where it matters, if that makes sense. And you know, to be general here, we could do something like a like an int16 constant. Note it's in 16 because it's operating, it's ANDing with this. So oh, sorry. We can make it constant, and we can call it bit mask, int 16 or something if we want. Something like that. And we can just generalize it. And if we need it other places, we can do this. Okay? It's also an option. Great, so now let's write to the left. After that, let's write to the right. Let's see if this will work. So now we're going to store in the left something, and we're going to store in the right something. And it's pretty cool because we can pack whatever we want. And again, we could pack, now I'm just doing it half and half, so maybe a struct is also a really good solution here. But you could imagine this red line was like here. My right side is only these 5 bits, and the left side is these, and so on. So I just want to make that clear. Okay, cool. So let's redeploy that. Again, we need to get the contract, not the library. Cool. So let's bit pack. What are we going to do? -1, -2. Okay, so now we get back from the left side -1, we get back from the right side -2. And you saw how the -2 does not overwrite what we have in the left side. Let me show you the wrong way to do it. Let's say we did not do the bit mask. let's say we just shift it, let's say we just cast it into an int16 and add it on top. The right side will now interfere with the left side. So we're first going to write to the left side. When we then write to the right side, it's going to interfere with it. So let me show you how that looks. So we're going to do this. Going to do this. Oh, again, it switches over. Okay, cool. So we're going to bitpack. So we're first going to write -2, but now the -1 will interfere. Yeah, in fact, we get an error, and we get an error because we're just adding it on top to the right. Let's see here. Valid big numbers here. Oh. Let me just see what's going on here. Did I do something wrong there? Okay, bitpack -1, -2, -1. Okay, I don't know what happened there. Anyway, so you see how we put -2 in the left side, and then when we put the -1, see, the -1 will still come out fine, but you see it has interfered with the stuff on the left. It's now -3, which is wrong. Okay, so just wanted to show you like why we're doing all that stuff. Cool. So we can write bits, we can read bits, we can pack bits, and you can imagine I just put 8. Again, I really want to emphasize that because it's very cool. I put 8 here, but you could put 4, you could put 3, so you can pack things together very succinctly if you can just represent it by 8 bits and so on, 16 bits and whatnot. And that's how it looks. All right, so I hope that this was helpful. This is just some cool stuff you can do and get full access to the exact bits that you need. I hope this was helpful. Feel free to subscribe, like this video if you learned something new, and play around with it yourself. There are a lot of other things you can do. Like I said, you can toggle bits, you can put a like overwrite and so on. Here I'm adding. There are a lot of other things that can be done, but these basically just comes down to different bitwise operators and stuff. But I hope you have the fundamentals, the visualization of what happens underneath, the falling off the cliff thing, like we can cut bits, choose complement we touched on. I hope that was helpful. So well, thanks for watching, and let me know what other content you'd like to see. This was something I needed recently in a project I did, so it was kind of cool to just do a deep dive on. But thank you for watching. All right, take care.